Thank you, and thank you for still being here. Okay, so I'm going to talk about some works that I did mainly during my PhD. And it deals with rational transductions, or I will call them sometimes rational functions. There are extensions of automata where you have outputs on the transitions. So instead of describing languages over words, they describe functions from words to words, or maybe sometimes relations. Okay, and I'll talk about minimization, so the good old minimization that you know for deterministic automata, and what it has brought for languages, and what it can and cannot do for functions or transductions. Okay, so the general theme is to transfer some well-known and loved results that we have over languages, and so transfer them to functions. Okay, so from functions from words to words. Okay, so the kinds of problems that I will be considering are definability problems. So very, very broadly speaking, I have two classes of, for instance, machines or formulas or whatever, things that describe, for instance, languages. So I could say that C1 is the class of push-down automata, and C2 the class of finite automata. Okay, and I could ask this problem. We know the answer to this one. So if I'm given some push-down automaton, M1, is there some finite automaton that recognizes the same language? Okay, so I'm given something in the class C1, and I want to know if I can express it in a different, often smaller class. So in that particular instance, we know that it's not decidable. But we will see some cases where we have positive answers for rational languages. Yeah, I say rational languages, so you can translate to regular languages if you prefer, but you would be wrong. So over rational languages, we have many different equivalent models. So the rational or regular expressions is one. Okay, so we have finite sets, unions, concatenations, and clean star. So I will use this example. So this would be the language of words of odd length. And we have finite automata. So they could be one-way deterministic automata or two-way non-deterministic or any combination of those, and they would still recognize the regular languages. So here, beautiful automaton. So this one is one-way deterministic. There's the formalism of MSO formulas. So, okay, I'll try. This is harder. So we want to say that there is a set that contains exactly the, let's say, the odd positions. So, let's say min of x. I'm using a macro here, okay. I'm cheating a bit. And let's say for x, y, if there's successors, then there's something like that. Okay? Okay. So the minimal position is in big X, the maximal position is in big X, and when I have two consecutive positions, they cannot be simultaneously in X or in its complement. Okay. And then there's a fourth one, which is recognizability by finite monoids. So, sorry? Yeah. Thank you. Okay, so I could take this morphism into the group of two elements, where I send the letter A to 1. And then my language would be exactly phi minus 1 of the element 1. Okay, all the words of odd length. Okay, so we have this beautiful picture with constructions from every corner to every other corner. And so here I have finite monoids, but I will also be talking about congruences. So they're very closely related, the two, of course. So if you want to have some picture in your mind, you could look at the transition congruence as associated with this automaton. What is it? Okay, we say that two words are equivalent for this automaton if basically they induce the same function over states. Okay? So I can go from P to Q reading U if and only if I can do it for V, reading V. Okay? And so this is the transition congruence of an automaton. And so what are the equivalent words for this automaton? They're exactly the words that have the same length mod 2, right? So two even words of even length will send 0 to 0 and 1 to 1, and two words of odd length will exchange 0 and 1. Okay? So this congruence, two words are equivalent in this automaton exactly when they have the same length mod 2. Okay? So you see the very strong connection between this and this. Okay, so that was for languages. And we're still in the realm of languages. So now we can look at some subclass of regular languages. Namely the star-free languages. So as the name suggests, we forbid using the star, the cleanly star operation, but okay, we add complementation to compensate. So it defines a strictly smaller, like a strict subclass of the regular languages. And I will be able to fill all these corners. So for automata, we have this notion of aperiodic automata. What's the main idea? It says that there is some number such that whatever the word, if I read this word many times, it's the same. I cannot differentiate between reading it a lot and reading it a lot. Okay? It's the same. After some point, reading a lot of W is always the same. Okay? So you can think also about these automata as automata that are not able to count modulo. Okay? So this one is able to count modulo. So reading a to the n and a to the n plus 1 is different for this one. Okay? Okay. I have nothing to write, but this one is not aperiodic. You see? Reading a to the n and a to the n plus 1 is different. Okay? And so then we have this very nice result that it coincides with first order logic. So exactly the same thing, but we don't have quantification over second order variables. And so here we do use it, and yeah, well, I'll say something else later. Okay, and then for algebraic recognizability, so it looks a lot like what we have here. And another way to phrase it in terms of monoid is by saying it's the monoids that are group free. So recognized by a group free monoid. So a monoid that does not contain a sub-semigroup, that is a group, except the trivial group. Okay? So we had the first, so we had this picture for regular languages, and now we have the same picture for a strict subclass. Oh yeah, and so this equivalence is due to Schützenberger for the algebraic part. So he showed this diagonal equivalence. And then McNaughton paper showed the connection with the first order logic. Okay, so now we can try to move on to functions and see if we have some similar patterns. So I will be talking about functions from finite words to finite words. I'll be writing input words in red and output words in blue to visually differentiate the two. So let's consider a very simple function. So this one just erases all occurrences of the letter A, so it's just a morphism. Okay, now I consider slightly more complicated one. So I take the first letter of my word, and every subsequent letter is replaced by this one. Okay? So for this I can define a transducer that will be realizing this function. Okay, so here I have a one-way deterministic automaton. It's very pretty. And so here you have the input letters, and basically it records what's the first letter of the word. And now what I do is that I add outputs to the transitions. Okay, so when I read the first letter, I erase it, I output epsilon, and then every subsequent letter is replaced by the first letter that I saw. Okay, so here I remember that the first letter was an A, and every letter is replaced by A. Here I remember that the first letter was a B, and every letter is replaced by B. So it does realize this function. And we can realize it by a deterministic automaton. Now we can do something that looks very similar, F last, where we replace every letter depending on the last letter of the word. And here I have a non-deterministic automaton. So at first I choose to start here if I think that the last letter will be in A, and I start here if I think the last letter will be in B. Okay? So I replace all my letters depending on my non-deterministic choice, and at some point I guess that I'm reading the last letter and I'm jumping to the accepting state. Okay, so intuitively this function f last, I hope you can see that it cannot be realized deterministically. Because you cannot, before you read the last letter, you don't know if you should be producing A's or B's. And since you only have finite amount of memory, when you've read 100 letters, you still don't know what you should be producing, and you cannot store unbounded amount of information. So this cannot be done deterministically with bounded memory. Okay. Then I have a slight generalization of last, swap, just exchanges the first and the last letter, which is also intrinsically non-deterministic, like last. And then I have something that goes a bit beyond the scope of this talk, this doubling function where I copy my input twice. So here, even non-deterministically, it cannot be done. Okay, so I have this picture of functions. So they have names that are questionable. So this class here is called the class of sequential functions. So the function that can be realized by deterministic one-way machines. So these two, for instance. Then rational functions, realizable by non-deterministic one-way machines. And regular functions where I need a two-way automata to realize these functions. So I won't talk about two-way automata much, but So it's just an automaton that can move both left and right on its input tape and outputs later. And so you can read your word, and when you reach the end, you go back to the first position and read it again to produce it twice. Okay. Is everything clear until now? Okay. So this is, so we see that the picture for function is much more complicated than for languages. For languages, deterministic automata, non-deterministic automata, and two-way automata all define regular languages. Okay. So as I said, the main class that I will be considering are these two. And so the class of rational transduction, I want to define, I want to obtain some kind of Depuis theorem, so equivalence between automata and logic for this class. So I have this notion of automata, and I'm presenting to you this notion of logical transducer. So how does it work? So you have a finite set of outputs. It will be the words that you'll be replacing letters of your input by. And okay, you have a formula for each of these words, and this formula phi epsilon of x tells me which positions x of my input should be replaced by epsilon. Okay, so if I take the positions that are a's or labeled by A or labeled by C, but if it's C, then it has to be the last position. These ones I replace by the empty word. If the position is a B, I double the number of B's. And if the position is a C, but it's not the last position of the word, then I just leave it as it were. Okay? And so for instance, this transition this function maps this word to this word. Okay, so the A's are erased, all the A's. The B's are doubled, and the C's are kept unless if it's the last position. So we have these two models, and so actually we have this kind of Depuis theorem. So we have the equivalence between logical transducers and this automaton model. Okay. So now I can ask, okay, what about star-free? So for languages, I had this class of star-free languages, and it coincided with first-order logic. So do I still have this correspondence between star-freeness and first-order logic? So that's what I want to explore. Okay, so but I'll explore it in a slightly more general way. Okay, so I consider F, which is a fragment of MSO. Okay, so a fragment of MSO just means I take only some formulas. So for instance, first order logic is a fragment of MSO. So every time you see F, you can think of first order logic if it helps you. Okay, and so the kind of problem that I want to solve is I have some MSO transducer realizing a function. I want to know, can I realize it in some weaker logic? Okay? So, for instance, I have an MSO transducer. Can I realize the same function in first order logic? So we could consider other fragments of first order logic, as I said, first order logic with two variables, which is also well studied. And we have this alternation, quantifier alternation hierarchy that if you're not familiar with, it's all right. And you could also add new predicates, like successor, of course, modular predicates, and weird quantifiers that can count the number of occurrence of some position satisfying a formula, or modular quantifiers, and so on. But so if you're not familiar with these weird logics, you can think just about first order logic. Okay, So how will I solve this problem? So of course I will be inspired by how this problem is solved for languages. So for languages, what is the first main ingredient to solving these kinds of problems is that we have correspondences between fragments of logic and what are called variety of monoids or of congruences. I won't be going into details, but if you look at first order logic, so it corresponds to it was on one of my previous slides. So I'll be writing here. So a periodic monoid. For okay, so an aperiodic monoid is a monoid of this shape. So there is a large enough power so that when you iterate an element of the monoid enough times, you cannot count modulo, basically. And so you have some equation that characterizes exactly these monoids. Okay, and you also have slightly more complicated equations for monoids that correspond to other fragments. Okay, so this is a quite generic and powerful tool. Okay, and we have a transfer theorem that says, okay, when I have a correspondence for languages, I can transfer it for transductions using some mild assumptions that I won't detail here. Okay. And yeah, I didn't tell you, but when I talk about the definability of a transduction given, so, okay. When is a transduction definable in A for aperiodic? I just look at its the transition congruence that I defined here. I want it to be aperiodic in the sense over there. Okay. Okay, so in the case of languages, for all the logical fragments that I gave above, the definability problem is decidable. Okay, so we have this correspondence between logic and algebra, and this helps us to solve the definability problem. So I will explain how. So in particular, it's also true for first order logic. So how do you do it? You use the syntactic congruence of the language, so also called Myhill-Nerodi congruence. So you say that two words are equivalent for the language if the residual of the language with respect to these words is the same. Okay, so what's the residual? So u minus 1l is all the words that I can read after having read u and end up in my language. Okay, so this is the syntactic congruence. And from this syntactic congruence, you can construct the minimal automaton of the language. So the initial state is the equivalence class of the empty word. Then when you're in the class of U and you read A, you go to the class of UA. And the accepting states are the ones, are the classes of the words in the language. Okay. And this minimal automaton, as the name suggests, is actually minimal in the sense that any congruence that recognizes this language has to be finer than this syntactic congruence. Okay, so finer in the sense that it will have more equivalence classes, or if you want to think of it in terms of automata, have more states, right? Okay. And so this minimal automaton you can compute using your favorite like Moore or Hopcroft algorithm by merging equivalent states, right? And the beauty of it is that merging equivalent states just gives you the unique minimal automaton. Okay, so I consider this automaton, okay, and I can look at the state 2 and look at what is accepted from state 2, okay, it's all the words. From state 3 as well, and from state 4 as well. So these 3 states are actually equivalent, because from being in 2, 3, or 4 gives you the same result. The words that you accept from these states are always the same. So you say, okay, these states are equivalent, so I can just merge them. Okay, it's very simple. And so this new automaton that you obtain from minimization is coarser than the one you had. So the one you had is finer. And it's actually the syntactic automaton. Okay, so that's pretty. And okay, where am I going with that? Okay, maybe I have something in this slide, I hope. Okay, so what are the ingredients to solving the definability problem? Okay, so I have this logic and some variety, so some class of congruences. And I'm given a language. I can compute this minimal congruence or this minimal automaton. And the very important part is that varieties are closed under coarser congruences. So this thing of merging the states will preserve satisfying these kinds of equations. Okay, so if my big automaton satisfies the equations, then minimizing it means I still satisfy the equation. So in order to know if there exists one that satisfies the equations, I just need to minimize it and check if the minimal one does satisfy the equations. Okay, so my language will be definable if and only if its minimal automaton satisfies the equations of the variety. So it is aperiodic in the case of first order logic. Okay, so that's the approach. Okay, so in particular it's decidable for first order logic. It's actually p-space complete, if you want to know. Okay, so can we do the same thing for sequential functions? So let me remind you, sequential functions are the ones defined by deterministic transducers. So can I minimize transducers the same way I did for finite automata, so deterministic transducers? So here I can look at the function that I realize from a state, and if two states realize the same function, I can merge them. Okay, that's one idea. So if I look at F1 and F4, so they realize almost the same function. There's just a delay of one letter. Okay, so if I start from state 1, I will accept words of odd length and will be dividing by 2, rounding up, right? And here dividing by 2, rounding down. Okay, so they're almost compatible. I want to say I actually want to merge them because they're very close to being compatible. So what's the main idea? Is that here from state 1, when I enter state 1, I know that whatever future execution I have, since the state 1 is not final, any execution will have to take this transition and produce an A. Okay, so this A that I produce here, I can push it back actually. When I entered state 1, I knew that I will always be producing at least one A. So I push all the outputs as far back as possible. So here my A is pushed there, and actually since I have a transition that enters here, I also push it back there. Okay, and so I do this for all the transitions. I push all the outputs back as far as I can. And then I do the same thing. If two states are equivalent, they realize the same functions, I can just merge them. Okay? And the same magic happens as for languages. So you have a notion of syntactic congruence that will exactly coincide with this minimization procedure. Okay, I can quickly give you the definition of the syntactic congruence. It's a bit scary. So I can define this f hat, which is the longest common prefix of all outputs of words that start with u. Okay, so f hat is this idea of pushing the outputs as early as possible. Okay, so I produce everything that I can, knowing that I have read the word u. Then I can define the residual, as for languages. So u minus 1 of f, when I apply it to w, it's f of uw, from which I take back everything that is due to u. Okay? So it's exactly the same idea as the residual for languages. I remove the contribution of u from f of uw. And then the definition is just two words are syntactically equivalent if they have the same residual. Okay? And so this construction is due to Chauffru. So there's a unique minimal sequential transducer. It's given by this syntactic congruence, and you can obtain it through more like minimization, like merging state minimization procedure. Okay, so in particular, if I want to decide if a sequential function can be realized by some aperiodic transducer, aperiodic sequential transducer. Okay, I assume if there is one which is aperiodic, I can apply this minimization procedure, and I'm guaranteed that this will not destroy aperiodicity. It will preserve it. So I'll minimize my transducer and just check if this minimal one is aperiodic. Okay, so that's very nice. Okay, but now we want to what we want to tackle is rational functions, not sequential functions. Okay. So what are the difficulties? So we have non-determinism, and this notion of minimal automata, it only works for deterministic automata. There's no nice notion of minimal automaton except just having fewer states, but you can have several minimal automata for the same language that have nothing to do with each other. So yeah, there's no nice notion, and hence, and also no good notion of minimality. So okay, let's take this function swap. So I remind you that it just takes the first and the last letter and exchanges them. Okay, so this function is not sequential, right? Because you have to guess what is the last letter before you can produce anything. Because the first thing you have to produce is the last letter. So you have to guess it and then check that your guess was correct. So what is the least amount of information that you need in order to, what is the least amount of additional information that you need to realize it from left to right? So in this case, the only thing you need is just what is the last letter. This is just, you just need this piece of information. So the idea is that we will label each position of the word by this additional information. Okay, we give just enough information so that reading the word from left to right, we will be able to produce this function sequentially. So let me show you. So here from this position, I add this information b that says, okay, the last letter will be a b. So here epsilon just says this is the last letter. Okay, and so here the information is really simple. So I just propagate this, and so I label every position by the information. By the way, the last letter will be a b. Okay. So now, when I read this annotated word from left to right, it's realizing this function is easy, right? When I read the first letter, I know what is the last, so I can produce it immediately. And then I copy every letter, except when I see this epsilon, I know that I don't have to produce this letter because I put it in the front. And I remember what was the first letter so that I can put it in its place. So by adding this additional information, now my function becomes sequential. Okay? And this annotation, I can produce it by an automaton that is not deterministic, but all like the symmetric of deterministic. It's deterministic from the right to the left. Okay? So if you look at all these arrows and you invert them, you have a deterministic automaton that enters the word from the right and just reads the word from right to left and labels each position by its state. Okay, so here I start in the state I have read nothing. Then I read a B. Okay, and I can annotate here. So I read a B and I'll label my B with epsilon. Here I read an A and I label my A with epsilon. And here, every letter that I read, I label it by my current state. Okay, so I read my word from right to left, and every time I take a transition, I annotate the letter by the current state. Okay, so this ID was okay. So what I want to tell you is that any rational function, actually, you can obtain this way. So first, a right-to-left deterministic function, then a left-to-right deterministic function. Okay. And so there's a model that doesn't use explicitly composition, and this model, okay, is a bit involved, but its nice properties is that it will have a minimization procedure that does preserve all the equations that we want. Okay. So hold on, I will be introducing this model of bimachines, and this idea is that you have both an automaton that is deterministic and an automaton that is deterministic from right to left, and you combine these two automata in some way. Okay, so this is scary. So I'm going to be reading a word, and in order to produce outputs, I'll be using two runs. So a run on the left automaton that reads the word from left to right, and a run on the right automaton that will be reading the word from right to left. And combining these two runs, I will be producing the output. So this right automaton, it starts in R0 with an A, goes to RA, and then it just stays there. Okay, so I have this run. Then I have the left automaton, it will start in L0. And now, when I have a letter, I have this information coming from my left automaton that tells me something about the past, right? This left to right automaton remembers information about the past. And here I have RA, which tells me some information about the future. Okay, it has read all this, and it knows some regular information about my suffix. So I combine these two states. I go to my table, and my output says, okay, if I'm L0 in my past, RA in my future, and the letter is B, I should output an A. Okay. Then I do this for all my letters. I combine the information from the past and from the future. And that way I can produce my output. Okay? And so here what this function does is exactly the swap function. Okay. Okay. So these bimachines, okay, they're kind of ugly, but they have these really nice properties that you can minimize them. So briefly, what's the main idea from this paper by Rationnelles and Schützenberger is that if you fix the right automaton, as we've seen, it corresponds to labeling the word with enough information so that the function is sequential. And for sequential functions, we know that we can minimize. We have a nice minimization algorithm. So you start by fixing the right automaton, and you can minimize the left one using the construction of Chauffru. And you can do it symmetrically, right? You can fix the left automaton and minimize the right one. And moreover, from this article, there's a unique minimal right automaton. Okay? So the least amount of additional information you need to realize the function from left to right. Okay? And if you combine these two results, okay, I won't go into too much details. If you combine these two results, you can obtain that actually for any rational functions, there's only a finite number of minimal bimachines. Okay? So you have this smallest right automaton, and it comes with a quite large left automaton. But you also have a small left automaton and a large right automaton. And there's actually a trade-off between the two. And so some of the computation can be done more on the deterministic part, some of it can be done on the right to left deterministic part, and you have this kind of trade-off. Okay, I won't go to the analysis. But now if you want to check first order definability, you know that, so it's first order definable if it's definable by some aperiodic bimachine. You can minimize this one, and you will end up in one of the minimal bimachines. So it's not unique, but you know that you will end up in one of the minimal bimachines. So to check if it's first order definable, you can compute all of the minimal bimachines, and if one of them is aperiodic, then you've won. The function is first order definable. Okay, and then, okay, it holds for other varieties. Okay, so a quick note on what other directions can and have been considered. So all the logics that it works with are logics that use the order, and this is kind of crucial because you need to be able to differentiate between this past and future information. Okay. So I don't know how to do it for logics that don't have access to this order. We have extended this work to infinite words, and okay, I won't go into the difficulties, but it's harder, basically. Some things go wrong, but still we manage to recover decidability. And then there's a very, what's the word? Okay, there's this that I think is quite out of reach for now. We don't have the good understanding of two-way automata, two-way transducers, and we have no way of minimization, no good notion of minimal two-way transducer to solve this problem on two-way transducer for now. So this would be really interesting, but I think we're quite far from it. Okay, and this is a simpler approach. So sweeping transducers are two-way, but they can only change directions at the ends of the word. So they're almost one way. Okay, so I think this is it. Thank you very much.
So we're short on time because someone booked the room, so maybe we can take one of the questions.
For the minimal machines, you say that there are many, so but for your piece-based completeness, so it means you can enumerate all of them?
Yeah.
And how many can you have?
Yeah, it's a good question. I think there is polynomially many. So because, oh no, actually. No, there might be, exponentially many. Yeah.
Another question? Well, maybe we can thank again. That's all.
Thank you.